Okay, thank you so much. Okay, so so first of all, I would like to thank you everyone for being here today. And in today's webinar, which is titled "Data-Driven Workflows in Oil and Gas Industry Using Python Ecosystem." So in this webinar, I'm really delighted to see so many of you. And in this hour, an hour and a half of a session, we are trying to make things straight and show you what are the things that are possible in Python and basically what's the fuss about Python and why suddenly everyone is starting to use it. So first of all, let's start with a brief introduction about the instructor himself. So my name is Nashat Omar. I've been working in oil and gas industry for a little bit over 12 years now. I started my career working for Schlumberger in oil and gas drilling wells, and then I transferred and shifted to production engineer and flow assurance afterwards. Now, currently, I'm working as a production engineering data scientist and consultant at the same time. So here are some of the things that I've published over the years. So in the past 4 to 5 years, I've managed to publish 7 technical papers with diverse background on production flow assurance, well management, and AI. Plus the contributions I made to the Python community so far and the oil and gas industry so far. It's basically, so far I've published 3 libraries this year. So one library is for well integrity, another library is for mapping, and another library is for multi-phase flow calculation. So without further ado, let me show you what are some of the things that we are going to see today and some of the rules that you should follow. Number one, you should never unmute yourself. That's number one. Number two, if you have any questions, feel free to ask it in the chat box, and I will make sure that every question is going to be answered. If you feel your question is out of the context or the question is not going with the flow of the session, that's okay. You can also ask that, and I will try to also dedicate some time to answer these. In today's session, we're not going to dive deep into Python. Number one, I'm just going to show you some of the things that you can do. And before we even go ahead and take the Python route, it's really important for me to show you what are some of the challenges we have in the oil and gas industry, and what are some of the things that are not possible that's pushing us to do data-driven analytics using Python and other tools. So first of all, we're going to start with a physical phenomena that are dominated by oil and gas flow. So what are some of the physics? Number two, I'm going to show you some of the classical solutions to oil and gas problems. Plus, I'm going to show you the link to modern data science and how we can do data modeling and data statistics. And I'm going to show you how to do regression and decision tree analysis, dashboarding, visualization, data science, data life cycle in oil and gas industry, and afterwards I'm going to show you the data formats we have in the industry and some of the challenges associated with that as well. And finally, we are going to finish up this session with some examples on how we can implement Python in oil and gas industry. So I will try to show you a couple of examples. One example that I'm going to try to show you is how we can create some data science calculations as creating some basic statistics with Python with few lines of code, and how we can create like interactive plots that are really powerful, much more powerful than what you can do in Excel. Finally, I will try to show you, if we have enough time, how you can automate some of the things that you can do in production engineering by connecting Prosper to Python and basically start to automate the full calculation inside Python without even opening the software. So without further ado, let's go ahead and start today's session. This session, by the way, a friendly warning, this session is going to be a session that's dense with information. It's going to be packed with information. So the recording will be there for you. You can review the recording later as well. So I am going to try to provide you with as much information as possible in this hour and a half. It's always your duty that you have to go back and then do some research and you do your homework to understand some of the concepts that are going to be presented. So now let's go ahead and start. In oil and gas industry, it's no different than other industries. All the industries in all the world is governed by 3 equations. This is at least to our knowledge. By the way, there are other equations as well, or these are called physical phenomena that govern all the industries. So The first governing equation that governs our industry is called conservation of mass. The second one is called conservation of momentum. The third one is called conservation of energy. And combination and intersection of these three equations is what petroleum engineering is about. So petroleum engineering usually works somewhere in here. So in this um, red triangle. So this is the intersection of these three equations. So what does these three equations dictate and how do they work and where do they work? So first of all, let me show you where these equations exist. Actually, these equations exist everywhere, and I mean everywhere. It exists in wells, it exists in flow lines, it exists in reservoirs, in process vessels, tanks, custody transfer. It even exists in your blood. If it even exists in your human body system. These equations are believed to, by the way, this is very important. These three equations are believed to be a part of a bigger equation that governs the full universe, which is known the theory of, or the unified theory of the universe, which is these three equations are part of that, but this is to our human understanding. So these equations usually they have some limitations. That's why usually we turn into data-driven analysis. Anyways, these concepts can be a little bit difficult, so that's why you have to go back and dig a little bit deeper into these. But yeah, oil and gas industry is governed by these three equations. So the general formulation for these three equations, they look like this. So you have one equation for mass, one equation for pressures, which is called the momentum, and one more equation for the energy transfer, or the energy transfer is usually the heat transfer equation. So once you combine these equations, you will get or you will yield a single unified equation, which is known as the Navier-Stokes equation. A Navier-Stokes equation is an equation that's unsolvable so far. No one have ever solved this equation because it's so complex. Plus, it describes the system in 3D. It's not easy to solve. Just keep that in mind. This is, or you can see this equation below, it's actually what governs every industry we have in the universe. Now let's move on. So what are some of the things that we can do in order to understand how to solve this equation? Of course, this equation, it's extremely complex. There is no computer yet that can solve this equation. However, they speculate that quantum computing can solve this. Anyways, before ever that computer comes into our desks, let's see how people used to solve or how people approach to understanding their problem. Because as you know, engineers worth nothing without understanding the data. So engineering is all about knowing data, analyzing data, and basically extracting some useful calculations within it. Otherwise, an engineer is just a theoretician. He's just making a theories without the data. Anyways, let's move forward. Let me show you some of the things that people used to do in oil and gas industry in order to try to solve that equation. However, we never approached to solve that equation only in the past 50 years. Anyways, so the first thing that people do in the industry 200 years back, so they started to do problem solving based on lessons. So what does this mean? It means that you can open up the stove you have at home and you can light up the propane gas with the lighter, and then the flame will start to show. If you make your hand close to that flame, you will get burned. Now, that's a lesson. A lesson is a pattern recognition in your mind. So people started to see patterns, they started to see recognitions in oil and gas industry. They recognized patterns, and those patterns were converged, actually they were narrowed down into lessons afterwards. So that's why some of the practices we got from the oil and gas industry is basically dating to 150 years ago. And these are basically the best lessons or best learned lessons from the some of the practices that we did in the oil and gas industry. So that's the first source of information or the first source of things that we will do in oil and gas industry. Now, whenever the human beings have started to evolve and we started to get calculators, so the calculators that you use in in college or the hand calculator that you use in college, actually that is a privilege. People did not have that in the 70s. They did not have that in the 60s. Having a calculator at hand in the 60s was considered luxury and it was extremely expensive and it was a really big machine. So yeah, once that calculator started to show on desks in oil and gas companies, things started to take turn from lessons learned into empirical methods. So, what do we mean by empirical methods? Empirical methods are just certain ways of analyzing data and calculating basically relationships between the data. And this is called an empirical relationship. There are lots and lots of empirical relationships. And one of the infamous relationships that is empirical and the oil and gas industry is built on top of it, it's called Darcy equation. So the Darcy equation, which is this equation, flow rate equals to the area. This equation, flow rate equals to permeability multiplied by area, dP over dl divided by viscosity. And of course, there is an extended version of this equation. So this equation was by Henry Darcy, and this is considered an empirical equation. Usually empirical equations has some certain limitations. So that's why no matter what we do, we are never close enough to solving this equation, because solving this equation means that you're solving this exactly. Once you solve this equation exactly, you will exactly understand what the problem is. But yet we have to solve this equation. Now, afterwards, once we have computers actually got more powerful, now we shifted from empirical approaches into something called mechanistic approach. A mechanistic approach, it's a way of solving the above equation or this equation, and then just basically just simplifying some of the terms. For example, if you cannot solve for, like, for example, let's say the density and the gravity, you can assume this constant. And then, for example, you can assume like any of these, like for any of these components, you can assume these as an empirical constant. Like you assume this as a C. And once you do this, you will simplify this equation. And this equation, it still represents the physics, but it is narrowed down to something close to empirical. So yeah, this is called mechanistic method. Of course, mechanistic method is much more accurate than empirical, and the empirical is much more accurate than the lessons learned. But yet, we have to reach something called the physical phenomena. By the way, the empirical equations and the mechanistic equations usually do something like this, which is called curve fitting. Basically, you relate two variables or multiple variables at the same time. You have the x and y. So the main idea is to drive an equation that basically best fits your data based on a certain error, which is the spread, or let's say the distance from the actual data to the calculated data. Anyways, now let's see one of the equations. I've already told you that Darcy equation is one of the equations that's built, or the industry is built on top of, and this is considered as a correlation. Since this is a empirical correlation, it means that it's based on some form of experiments, but the data for this experiment was not quite enough in the modern day standards. So there are certain assumptions to this equation. You can see it needs to be, the fluid needs to be compressible, single phase, isothermal homogeneity, wettability is neglected, and most importantly, it was limited data set. But here is the idea. If you project these facts into today's standards, almost all of these are non-applicable to our oil and gas industry nowadays. But there are some certain extensions to this equation in order to make it work. Just keep just keep in mind these limitations that we have. Because based on these limitations, later I'm going to show you why do we need machine learning and why we need artificial intelligence in the first place. Just keep in mind these limitations that are basically coming from the early days of engineering. Now let's move to another equation in oil and gas industry, which is called the API 14E RP equation. This is coming from this API 14E standards. This is a standard for recommended practice, design and installation of offshore production system. So basically what this equation is, I know the name seems fancy, but there is one thing that you can do with this equation is to check something called an ERV. An ERV is actually called an erosional velocity ratio. So basically, whenever your fluid is faster than this ratio that you calculate, it means that you're trying to basically erode the pipe, or there will be a mechanical corrosion in your pipe. If you're below this, it means you're good. Anyways, this is a correlation that was proposed by SPE. I think it was in the 80s, and then it was revised in the 90s. Now, just take a look at this equation. This equation contains two things. It contains the C and contains the density. Now, basically, the things that you see in these types of equations are going to be the key point that you will do in machine learning and artificial intelligence because these limitations usually will push people to start data-driven analysis. Just keep, just keep your attention. So the C is called an empirical factor. Now I will show you where you get this from. And the density, it's called the row mixture or the mixture density. Now here is the problem. In order to calculate the ER, you need to know both of these. You can think that calculating density is easy, but to be honest, it's never easy because you never know the actual distribution of oil, gas, water, and maybe you have some hard materials as well, like sand, like asphaltene, like wax deposition. You never know truly these because a certain pipeline they usually have these sort of distributed fluid, and the fluid is not easily distinguishable like I am drawing. Sometimes it's just chaotic. Anyways, so let's say that under the assumption that we know what the density is or what the actual density is. Now this leads us to the next parameter. We need to know the C in order to calculate the erosional velocity. Now this is where it comes the absurdity of these types of representation. Usually in the standards, it assumes that the C is somewhere between 50 and 250, sometimes even above than that. Now, depending on the type of fluid you have and the type of the alloy you have and how much metal you are degrading over time. Now, no one in the oil and gas industry knows the exact value of the C. Of course, the more C you have, the more erosional velocity you will get. And the lower C you have, the more conservative result you will get. So it's really, really hard to tell if your calculation is correct. Why this is happening? Because this is happening because there was lack of data back in the 80s whenever these equations were proposed. Computers were not powerful enough, CPUs cannot do lots of calculations, and that's why these types of equation usually comes with a hefty limitations. Although these equations are really easy to use, but let's see what are the limitations for these sort of equations. Number one, these equations are only designed for single phase flow. It means that if you have multiple phases, the applicability of this equation can be uncertain at best. Plus, there is no alloy consideration. It means that this equation does not take into consideration the type of alloy that you're going to use. But most probably, this equation was built on carbon steel. Plus, limitedness of corrosive agents. It means that this equation cannot detect if you have CO2 or H2S. Plus, it cannot detect the electrochemical interactions that happens inside the fluid and the metal. Plus, there is no protective film consideration. Now, why I am showing you all of these? Let me show you the upcoming slides and then you'll understand. So, as I presented earlier, you saw that there are some limitations, or actually there are some severe limitations in the equations that we have at hand in oil and gas industry. I'm not saying that these equations are not good. This is what the industry is about. The industry is about trying different methods, tuning the equation in order to best fit the data. But the problem is what we are trying to do is we are trying to patch these equations. This is what we are trying to do. Introducing data science. Data science is a big umbrella of mathematics, statistics, programming, and most importantly, which people miss, is the domain knowledge. I have been teaching data science, Python, and data analytics to professional oil and gas engineers for over 5 years. In under no circumstances I ever encourage people who just graduated college into going into these sort of trainings I do. Because the trainings I usually do on data science and domain analytics, it assumes that you have 5 years of experience in oil and gas industry. Why these assumptions exist? Because of this point, which is domain knowledge. So whenever you see someone on LinkedIn or someone or on any forum on the online, and you see them doing oil and gas analytics, and they don't have any experience in the oil and gas analytics, it means that they are lacking the proper experience to understand what the data is about, what they are going to get. If you have domain knowledge in the oil and gas industry, and the domain knowledge can be anywhere between 3 to 5 years, then you're more than eligible to start targeting and learning data science. It's extremely crucial to have domain knowledge. And laterwards, you will see why. So the data science is all about extracting insights, pattern, creating equations, correlations, constructing relationships between the unknown parameters in the oil and gas industry. In order to be good at data science, you need to be good at computers, you need to be good at mathematics and statistics, and you need to be good about domain business. Okay? So, under no circumstances a person that graduated from computer science is going to do machine learning for oil and gas industry. That's just not possible. Why is this? Because he lacks the proper knowledge of the data. He does not know what these data represent. He can succeed under the supervision of someone who works in the industry, but never he can do this alone. Now, let's flip the table. Imagine yourself you're trying to build a model, or you're trying to do analytics for finance, or you're trying to do analytics for the human resources, or you're trying to do some analytics for some humanitarian organization. At best, the analytics that you're going to get are going to be very primitive with no insights from it because you don't have the domain knowledge. So, I cannot emphasize enough on the availability of the domain knowledge. If you have the domain knowledge, you'll be extremely successful. If not, first of all, learn the domain knowledge and then start applying the data science technologies that I'm going to show you. So this is what the data science is filling the gaps. It's data science is never about replacing the oil and gas industry. It's about filling the gaps where the original equations failed to predict something. So the whole idea of data science is about prediction. Prediction is the process of forecasting or estimating what the future event is going to be. So for example, if you want to know what's going to happen in, for example, in your oil and gas field tomorrow, or let's say next month, you need to know what happened in the past. Knowing what happened in the past might help you to know what's going to be happening in the future, and this is called the prediction. The prediction is actually it's an engineering judgment, and it's an educated judgment that we do in order to estimate or in order to know what's going to happen in the future. Because if we know what's going to happen in the future, we can do some of the things about the problems that might happen. We can mitigate the problems, or we can minimize the effect of the problem, or in the extreme cases, we can eliminate the problem altogether. So these are some of the things that you can do with the prediction. So actually the prediction, to be honest, it's not a new thing. Prediction started with the Babylonians and started with the old Egyptians, or they started with the Pharaoh Egyptians. So basically, these two communities, they, especially Babylonians, they used predictions in order to estimate the location of the moon and the location of the stars. Uh, this is back 4,000 years ago. Around the same time, Egyptians did the same thing. Egyptians, they predicted the flood of the River Nile because back in Egypt, at that time, River Nile was so large and it was so powerful, it flooded their crops. So the crops, the crops is in Arabic. It's called mahsul, which is the thing that you like agriculture of like corn or some form of wheat, and this is called crops. So these crops usually get flooded really frequently, especially in the winter, because the river Nile level starts to climb up. That's why the Egyptians used some equations to predict the river Nile flooding. So that's why prediction is not something new. Now, once you combine these two things, once you combine data science and domain knowledge, now there is a new thing emerges, which is called domain data science. So domain data science, it's an engineering or technical person like me and you guys. So basically he's specializing in a certain domain, and then he transfers into maths, statistics, and machine learnings. Once he do so, the idea behind this move is to start filling the gaps or apply some of the analytics that are not available to the oil and gas industry directly because it requires some data manipulation or let's say some data analytics. So the key idea from this slide is I need to let you know that there is a new position in the oil and gas industry, which is called domain data science. And in the Middle East, we already have some companies has started to apply this. For example, in Iraq, we have some people who are working in this. In Kuwait, we have. In UAE, in Qatar, we have some people who are working as domain data scientists. And this is going to be emerging emerging position as we go forward. So it's extremely important to know what this is. A domain data science is just basically a person that knows a certain domain in the industry, like drilling, production, refining, distribution, business analytics, or any types of these domains that are related to the industry. And then he applies the skill set that he learns on data science in order to transfer the data into actual insights in the oil and gas industry. Now, let me show you before we move forward to more complex approaches in data science and especially AI and machine learning. Oil and gas industry have emerged from really basic methods of analyzing data and understanding what's happening. So these are the modeling approaches that happened in the oil and gas industry, and it was a natural evolution of the technology evolution we had. So the first thing that we had in the oil and gas industry, it's called the heuristic methods. So the heuristic method, this is not just in the oil and gas industry, this is actually in all the industries. Heuristic methods are sets of methods that you apply and they work fine. But the problem is we don't know why they work. So the heuristic method, you can see them or you can perceive them as lessons learned, but we don't know why they are working. Let me see if I can think of an example of the heuristic methods. Uh, Actually, I cannot think of an example now. Maybe down the road, if I think of an example, I will show you what this is. Now, once we surpass heuristic methods, now we will move to something called rule-based systems. Rule-based systems are just an equation programmed, or let's say an equations that are used and programmed based on some certain rules that we do. And when in college, 99% of the things that you studied or the calculations that you studied are rule-based systems. So for example, there is a certain procedure that you saw in the college, which is to calculate the drilling hydraulics. That procedure is based on something called rule-based system. You set rules and then you will do the calculation based on these rules. Okay, now just keep that in mind. You will do the rules, you will set the rules. So now, number one, the human sets the rule. Number two, he solves equations. Or, well, he or she solves the equation. And number three, you will get results. Just keep in mind, this is extremely important. Number one, human sets a rule. Number two, solve the equation. Number three, get the result. Now, an infamous example on this will be this. For example, let's assume that we have an oil field. So this is an oil field. So the pressure, sorry. So the pressure for the oil field, let's say it's 3000 psi gauges. And let's say the bubble point pressure, it's around, let's say 3900. This is just an example. So if you want to calculate the productivity index or the inflow performance for this field or as well within this field, which is more properly. So let's say that you want to know the IPR for this well. What you will do, number one, you will set the rule. So the rule is if reservoir pressure is greater than P bubble, I am going to use IP equation, or sorry, the PI equation, which is Q over delta P. Now, there is another rule. If the bubble point pressure, or the PB, is greater than the reservoir pressure, sorry, actually this, yeah, it's greater than the reservoir pressure, it means that you're in two-phase region. So that's why, for example, you can set another rule, like use Vogel equation, which is Q over Q max. equals to 1 minus V or minus V over pressure ratio over pressure ratio. So this is the Vogel equation. And if you want to know what the V is, please go ahead and read some of the papers from the 70s about the Vogel coefficient. Anyways, this is the generalized form of the Vogel coefficient. This is what the rule-based system is. And number 3, we are going to get the results and maybe do some analytics afterwards. This is the rule-based systems. Now, regarding the statistical analysis or the statistical approach, this is the method. This method is used whenever you don't have enough data. So what do we mean by not having enough data? Let me show you an example. I'm going to pull an actual example to make this a little bit clear, because sometimes these are not very clear, especially for the people who are just kicking their career in the oil and gas industry. So let me show you what you can do with the statistical analysis. Okay, so this example that I'm going to show you, this is called a Monte Carlo simulation. A Monte Carlo simulation, it's a statistical way in order to evaluate the uncertainty of something. So for example, most of you guys, you know that there is an equation that's called the initial oil in place. The equation looks like this. The equation is not, it's not that hard. The equation is actually the volume of the field multiplied by the porosity. By the way, you will see different versions of this equation, but this is the most abstract version that I can give. Multiplied by the porosity, and then multiplied by the oil saturation, and divided by BOI. This is the most simplest version of the initial oil in place. So the volume multiplied by the porosity, multiplied by the oil saturation, and multiplied by the divided by B oil. Now, if we decompose these things, for example, the volume is nothing special but the pay zone thickness multiplied by the area of the field. Porosity is just porosity, and water saturation, oil saturation is the hydrocarbon saturation. Now, here's the problem. Usually in the oil and gas field, the layers we have, or the geological layers we have, it's subject to the deposition uh, basin that we had in the previous geological ages, like 200 or 300 or 500 years ago, or 500 million years ago. And the layers most definitely are not going to be the same height, and they are not going to be the same depth, and they are not going to be the same angle. So if you drill one well at the top of the formation, or at the top of the structure, you might get like 50 feet of pay zone. But if you go down, for example, you might get like 10 feet. Now, the idea is, how do we know which value is more representative to your field? How do we know if the 10 is correct or the 50 is correct? Or maybe there is a value in between that's correct. Now, this is just one parameter. This is just for the pay zone thickness. Now, what happened in the area? The area is much, much more harder to know. The areal of extension, or the areal extension of the field, it's extremely hard to determine. By the way, there are some certain fields in Middle East, they are still scanning the field and they are still adding some portions or the newer extensions to the field, because it's extremely hard to know if your field is fully connected or not. So that only comes as you produce and you do some more analytics and some more pressure survey, or let's say production survey jobs. So the area is also uncertain. The oil saturation is also uncertain. The only certain thing that we know about is the BOI, and the BOI usually gets uncertain, especially if your field is segmentized, or we know this as compartmentalization. So it's a compartment reservoir, or you can think of a reservoir you can think of your field as multiple sections of the field, and then they are combined together. But each of these can represent a field of its own. This is called a compartmented reservoir. The idea is, this equation, it's extremely hard to determine exactly. We don't know what the exact original oil in place is. So that's why you will do something called Monte Carlo simulation. So Monte Carlo simulation, it's a way of simulating different results based on predetermined core data or well-logged data. So this is what usually you will get. And you can, of course, expand this further as you go down. So for example, what I'm doing in this equation, I am assuming multiple H values or multiple page zone thickness values. I'm assuming multiple porosities. I'm assuming multiple water saturations. By the way, water saturation is not something special. Water saturation is more, it's 1 minus SO if you don't have any gases. So you can convert easily between these. And then you will combine the effect of all of these three into just a single original oil in place. And then you will evaluate the most probable value you will get from the simulation, which is going to be the peak value on the top. Now, how do you calibrate this model? This model can be calibrated the more wells you drill, the more logs you do, or the more pressure surveys you do, the more samples you will get, the more refined this model will be. But at certain stages, if the field, the reserve will be changing. So let's say that you have a field of, let me open the plotting application. Let's say you have this field, and this is what your field looks like. And this is, let's say this is a new field. You just acquired this field. Okay, and now you see that, for example, there are only 3 wells in this field. The problem is, if this field have a dimension of, let's say, 10 kilometers by, let's say, 5 kilometers, that will be 50 kilometers square. So in the area of 50 kilometers square, you only have 3 wells. It means that you only have 3 values for SO, 3 values for pay zone, and 3 values for, if you have 3 different samples of PVT, you will have 3 values of BOI. But certainly this is not going to be the case always. Now, how can you judge a field as big as 50 kilometers square based on these 3 points? So that's why you will turn into something called statistical modeling. The more wells you drill, the more repeated results, or let's say the more different results you will get, because the results will get more refined. You will start to cover more of the field. You will get like other wells covering different certain areas in the field. So the answers will get better over time. But yeah, reserve evaluation based on a statistical approach, it's a continuous process. This is not just in the beginning of the life of the field. No, as you progress in the production and as you progress drilling the field and developing the field, these equations and these plots will be reevaluated on yearly basis. Now, this is what the statistical analysis is, and usually we use Python for these types of things as well. Now, finally, once we have all of these things covered, we will move to something more advanced and more modern, which is called the AI. So the AI is short for artificial intelligence. The AI can be machine learning or it can be deep learning. And you will know what the difference is between these two. Just keep in mind this thing, which is called the rule-based system. Just keep in mind, first of all, the human sets the rule. He or she solves the equation based on him or his or her rule, and then you will get the results and some insights possibly. This is what the rule-based system looks like. Usually you will have a certain workflow that you go and follow. By the way, this workflow I'm getting from this is a H-Brown algorithm from the technology of artificial lift uh, by Brown, and this is an old book. So I already have the book in a PDF format if anyone wants that as well. So this is a rule-based system. You have a certain rules, you follow a certain algorithm, and finally, for example, you calculate the results. Okay. Uh, Softwares like Pipesym, Petrel, Eclipse, CMG, all of these softwares use rule-based system. For example, Pipesym uses this algorithm, and other well testing packages as well use this algorithm. Now, let's move on to the artificial intelligence. So now, what is artificial intelligence? Artificial intelligence, or let's say the machine learning and the deep learning, is the process of making the machine to invent his own rules. So what do we mean by this? If you remember that we said that rule-based system, it's 100% what's being taught in college nowadays for all the engineering disciplines. These rules that you set, these are subjected to change, and usually the change is based on engineering judgment. This is happen or these things happen whenever we set the rules. But sometimes there are some hidden rules in the data. So these hidden rules, you cannot learn these rules effectively as human beings. It's because it's extremely hard to analyze millions upon millions of data points. So that's why people in the 50s and as early as the 40s, they invented the earliest machine learning algorithms. And you'll understand what these are. So the idea of AI or idea of machine learning is to let the machine decide what rules he or she wants to use or what rules are set on certain data and superimposed on the data itself to get a certain answer. One more time, machine learning is just to teach or just to let the machine learn on his or her own. This is what the machine learning is about. So, machine learning is a predefined steps of rules or let's say steps of modeling processes that we do. For example, number one, we get the data. Number two, we clean and prepare the data. Number three, we train the model or let the model learn on its own. We will test our model and then we will try to improve. This is what the workflows of the machine learning looks like, and this is the overall workflow. And you can contact the webinar organizer for these charts because I already sent them these files. Now, let me show you what are some of the things that you can do in machine learning. As we said that machine learning is the process of allowing the machine to learn on her or his own. So this is usually what we do. There are lots of use cases that we can do and allow the machine learning to learn. For example, in 1960 something, a paper was published by Dugan. This paper actually showed how to know which gas wells are online and which gas wells are basically suffering and they're going to die. So the problem in the gas wells are usually called liquid loading problems. So the liquid loading problem is basically a liquid accumulation in the bottom hole. And based on that liquid accumulation, you will know if the well is going to die or the well is going to survive in the upcoming production time frames. So they did a certain analysis on the data, and of course the analysis were very primitive back then. And they concluded something. They concluded that if the gas flow rate is more than something called terminal velocity or the terminal rate, then the gas we can consider the well is unloading or producing properly. But if the flow rate is below a certain rate, which is known as the terminal velocity, one more time, then the well is not very good, or it might die in the upcoming uh, production time frame. Now, here is the idea. The equation looks like this. Terminal velocity equals some equation based on Stokes equation, by the way. But the idea of comparing your data or comparing your production data to this VT or the terminal velocity, like greater than or less than, this yields two rules. One rule is whenever this condition applies, which is true. Another rule, whenever the condition does not apply, which is false. This is called binary analysis. A binary analysis is very common in oil and gas industry. And one of the binary analysis that we usually do is to determine the pay zone thicknesses or the pay zone eligibility based on the gamma ray. So whenever in the oil and gas industry you compare two things, usually the answer is going to be either yes or no. So that's why this analysis generated a chart that looks like this. Anything above this line, it's good, or let's say it's true. Anything below this line, it's false. So it means that your wells are either good or bad. But we know from the fact of the experience that the wells can be good, can be bad, can be average performing, or it can be near good, or it can be near bad, or it can be extremely bad. So there is a spectrum of labels that you can give the wells. It's not just about good or bad. These types of analysis deem really limited with the current day operations that we have in the oil and gas industry. So that's why in machine learning, if you feed the same data to machine learning not just it's going to show you the problem with the well, but it's going to also label it for you. It will tell you what the problem with the well is. Because the machine learning, one of the things that you can do with the machine learning, it's called multi-label analysis or multi-class analysis. So what's multi-class analysis? You will insert the data, full data for your well, and then machine learning will start to predict what the condition of this well is going to be based on different factors like wellhead pressure, the bottom hole pressure, the fluid extracted, and the temperatures, and anything that you can think of. Machine learning will take, it will learn based on this, and then it will set its own rule. Now, the figure that you see in front of you, it's I a figure I generated, and this is based on wellhead pressure for gas wells and test rate for gas. So once you plot both of these, this is just plotting, and the colors that you see, these are the conditions for these wells. Daria parmas nona. So these colors shows you basically where the problematic area exists and where the actually wells that are not good are. So for example, you can see this portion of the data, it's questionable. These are unloaded, it means these are good. This is bad. But if we put this chart side by side to the other chart that was produced in the 60s, you can see there is certain sophistication that happened over the years. This is not because I built this chart. No, the method has been evolving very, very much. So we said that this chart had a single line. Anything above this is good. Anything below this is bad. But the same data, I applied the classical analysis to it. I took the same data and then I created another analytics with this based on machine learning. This is what the machine learning give you, and this is what the typical analysis gives you. So basically, the machine learning has the capability to learn from your data and set its own rules, and based on these own rules, it will start to predict the future for you. Now, this is on the right hand side is the classical analysis. So this is the classical analysis, which is called the Turner rate. Nowadays, it's called the Turner rate, and this is the machine learning driven analysis. Now, let me show you another example. Usually in oil and gas industry, it's extremely hard to generate labels or generate groupings. So for example, if I give you a certain number of wells or a certain number of operational data, only and only the experienced engineer with, let's say, 20, 30, or even 40 years of experience can know true and fact which one is good and which one is bad. And sometimes he also going to have some certain mistakes that he's going to go because this topic is very, very, very subjective. Being subjective, it means that it depends on someone's opinion and someone's experience. So let's say that I am going to give you wellhead pressures, flow rates, oil, gas, water, subsurface parameters, porosity, permeability, density, and anything in between. Let's say that I'm going to give you 10 columns of data. Your human brain, it's not going to see any patterns in the data. If you plot these, you're also not going to see any patterns because in the plotting process, the maximum plotting you can do in the Cartesian chart, it's going to be 5 dimensions plotting. So one dimension is X, another dimension is Y, another dimension is the color, like these. Another dimension will be size of these bubbles, as you see. And the last dimension is going to be the symbol, or is going to be the shape of these things. So the maximum you can do is 5 dimensions. But what happens if your data contains like 10 dimensions, 15 dimensions? You're not going to be able to plot these or see these in visuals. So that's why if you want to judge something or if you want to group something based on its data and the data volume you have is large and multiple columns like 10, 20, 50, or sometimes even, by the way, modern companies like Meta, like Alphabet, like Google, So these companies usually they build models based on hundreds upon hundreds of columns, but based on the customer behavior. So the same thing can be done in oil and gas industry. We will take all of these columns, we will take all of these data, we will insert it into a machine learning model, and we will tell the machine learning model or the AI model to group these data based on logical grouping. And once you train the model and model understands some certain rules in your data, it will start to create groups like for you like this. It will show you different groups. Knowing these groups, it's extremely hard, number one, as a human beings. Plus, there is no single equation in oil and gas industry that can create these types of groups for you. Now you can see where does the data science and the data-driven analytics, it's going to fill the gap. Now let's take another example. The same groups that the machine learning suggested for you, or the machine learning showed you that there are certain groups, what you can do is you can take these groups and you can take the names of the assets or the names of the wells and then superimpose that on the historical data. Once you do that and then start to plot the groups, you definitely going to start to see a pattern. It's as simple as that. Get something from machine learning and then superimpose that with the already domain knowledge you have. Now, let's move on to another example. So, for example, let's say that for now, oil and gas industry, we have something called ESP, which is electrical submersible pump. And usually, in order to do the analytics for the ESP, usually we have some ways of doing let's say, the evaluation for the ESP. So let me show you. So let me see. So there is something called failure analysis. Sorry, not this one. So there are certain charts that look like this. This is actually a daily run. Anyway, there is a certain thing that we usually do for ESP analysis that basically show us that what is the problem that we have at hand. So let me show ESP problem diagnostics. So usually we have a chart. So I don't know oil. Well, uh, there we go. This is the chart. This is the infamous chart that we have in the industry. Based on this chart, you will know what the problem is. For example, if you have a broken shaft, you have a hole or the punch in the tubing, you have a problem with the surface uh, uh, equipment, maybe you have a blockage in the system, maybe you have some stages that are going bad, they are wearing. So basically, these are the things you have. But you can see that this is a really rough guideline. It's just showing you symbols like this is going down, this is going up, this is staying still, or this is tripping. But the problem is you need to provide these rules manually in order to know what the problem with your ASP is. But you don't have to do that because if you use machine learning for this, not just you will predict the problem, but you can also forecast the problem before it happens. So once you insert the ESP data into machine learning or AI, basically you will get zones like this or charts like this. This is basically called a decision boundary chart. A decision boundary chart basically shows you wherever the problem is going to happen. For example, this is a certain problem area, this is another problem area. So you can get the boundaries for these problems. And then once you get new data for your SPE, you will know what the problems that's going to be happening. This is called early failure detection. This is regarding the SPA. There is another example that you can do. It's called data synthesization, which is creating well logs or missing well logs based on previous well logs data. So for example, let me show you. Let's say that we have this section of the field. Let's say you have 4 wells in this field. And what you can do is, for example, let's say that these 4 wells, these 3 wells, they all have the sonic log, the DT, but this well, they have a log for it, but they are missing the DT. So the DT is gone missing from this one, or they did not their own job. So what you can do is you can create an AI or the machine learning model that basically takes the DT from these, and then based on the other parameters, you can also generate a DT for this well. This is called generation of well logs. Now, how accurate this model is depends on how much data you have. The more data you have, the more accurate it is, but most definitely it's going to be better than having nothing. So this is the main workflow for digitization and synthesization of well logs. Number one, you will start with a large group of last files, and then you will insert these into Python. We will use Python, we will use pandas, we will use scikit-learn. So all of these libraries I'm going to try to show you afterwards. And then you will start to generate a full spectrum of well logs, and then of course you are going to match your data. And so the curves that you see, the green curves is the actual curve, and the red curve is the calculated curve. And you can see they go very nicely. You can see there are some areas in these, you have some separation in the result. That means that they are not converging very well, or they are not predicting very well. So the last three wells that you see on this chart, the last three ones, these are actually the parameter that we are doing is totally missing in this. So this is fully being generated in these wells. So these wells are not seen by the computer. Once we train the computer, we will show these wells and we'll tell it, well, try to predict these. Once it predicts, now it starts basically to show you what the values can be. And of course, you will match that with the original data. And if it's good, you can publish the model and basically tell everyone, well, if you have missing data, you can use this model. So one final thing that we will left with is everything that I have talked about. It's not possible without a proper storage. So what do we mean by storage? A storage is basically in oil and gas industry. It's called a database. A database is just a container that contains your data. So this is what the data you will get usually from oil and gas field, from different operators, and from different leases, or let's say from different facilities. So an oil and gas engineer, what he usually does, it basically he sorts out these data depending on the type, depending on the category, depending on the well, and on the asset. Basically, once he organizes these data, these data upon organization, they will be converted into something called a database. If you have a proper database, then you can do all of these modern analytics that I showed you. If you don't have a proper database or your data is not clean, well, you're going to have a real hard time into applying what I've just showed you. So this is what we have now for the theory. Before I go and move forward to showing you some applications of Python, we will start very simple. If you have any questions, please feel free to ask it in the chat box. Try to ask it in the chat box. Do not unmute yourself. Ask anything you have in the chat box. I will try to answer that before we even move forward to the coding session or the coding part of this. So any question is welcome, but I don't see any questions being asked yet. So one of the questions in the chat box about using the data and dealing with large data sets. Okay, so large data sets in oil and gas industry is now a common thing. It's not, let's say, it's not an obscure thing, or it's not something that you don't see quite often. As a matter of fact, let me show you a data about real-time drilling Let me show you one data. And this is not actually, this is not even the largest data that I have. So let me show you. By the way, these data sets or really large data sets, you cannot open these with Notebook. And by the way, you cannot open these with Excel as well. Excel cannot open these files because they are too large. So you can see it's already slow, but I'm going to try to show you the row counts on this data. So this is a real-time drilling data. You can see it contains something close to 400,000 lines of rows with something close to 100 columns. So it's really large data. Now, how can you deal with these types of data? In Python, luckily we have lots of libraries that can help us in this. But if you try to read these manually, you will suffer and you will have really hard time. So the libraries that I usually suggest for large workflows, you can use pandas. There's a library you can use called pandas. You can use this if you have like moderate amounts of data, like something close to 500k rows with a minimum number of columns. You can use this. Anything beyond that, you can use something called Dask, and you can also use something called polars. So these two are really new libraries in Python. They allow you to work with big data. So this is regarding the plotting, sorry, this is regarding the data visualization that you will do. But usually, whenever you have real large data sets like 2 million lines, 7 million lines, by the way, I have that data set that I'm working on. It's 11 million lines of rows. It's a production data. Usually, these types of data sets needs to be cleaned really well in order to reduce down the data. Once you clean them, you will resample them. Once you resample them, if the data chunk is manageable, you will start to train, but you have to wait lots. If you cannot do any of these, if you cannot resample and you need all of these 11 lines, usually your laptop, it's not going to be sufficient. You would need a calculation server for this. The company usually you work with, they will have some form of calculation server with multiple processors and something like 500 gigs of RAM. Yeah, 500 gigs of RAM, not storage RAM. So these companies usually can process these types of data, but you cannot do this on your personal PC. That's why you have to resample. So these are some of the techniques that you do. But these techniques, no matter what the technique you select, it's going to be based on these three libraries: Pandas, Dask, and Polars. So we have two more questions regarding the ESP diagnostics. So for ESP diagnostic, yes, you have to have sensors data. Otherwise, you cannot do any diagnostics because it's not a guesswork. You have to have real-time data. Once you have real-time data, you have to clean the data and you have to label the data, which one is problematic and which one is normal. Once you do this, and then the machine learning can help you in setting its own rules. Now, regarding the liquid loading, like setting valve or any method to solve it, yeah, the liquid loading can help you definitely, or the method of analyzing the liquid loading in gas wells, it's going to definitely help you to eliminate that, but it's not going to suggest you what solution that you have unless you label that as well. Yeah, Mr. Ibrahim is asking, can we use Python for solutions like failure blowout? Yeah, you can use Python for anything as long as the data is correct, the data is clean, and you have a label. By the way, there is something that you should know about machine learning and AI. I think not everyone is speaking about this, but you have to know this. Let me show you an example. Let's say that we have this really simple table. Okay. Let's say that this is a drilling table. It's going to be very simple. I will have time as a column. So this is the time as a column, and just going to show you like the bypass time: 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, as the time of drilling goes by. For example, we have the weight on bit, we have the rate of penetration, we have the mud density, and we have the amount of pump mud we have, which is going to be usually SPM or stroke per minute we have per pump. Usually these are going to be a table like this. This is usually comes from a real-time drilling system. By the way, which we usually have. We also have these in Middle East. This is not very uncommon. We do have these. So once you have full data on these, so you have everything filled up. So what you can do, you will provide this to an engineer that usually works in the rig or works in the office or in the HQ. So what he's going to do, he's going to analyze these data. So for example, he sees the data of the first time step. He will say this is normal data, no problem, normal, no problem. Sometimes what they do, they only label the data that have problems. For example, you can say that potential flux to the well, you can say potential loss, and so on and so forth. Now, providing the names to the problems, this is called labeling in oil and gas industry. Well, in machine learning, this is called labeling. In oil and gas industry, this is called events. But if you don't have these events, you cannot train proper machine learning for failure analysis. If you have these, you can go and train. If you don't have these, you have to make these and then you will train the machine learning model. This is not every people are speaking about this, but yeah, this is one of the limitations of having AI. Anyways, I think we don't have any more questions. Let's now move forward. So, making machine learning model interpretable, making flexible. Yeah, for the model interpretability, in order to make your model being able to interpret the model, now we have two approaches. Basically, if you asked this question like 5 years ago, I would tell you that in order to make the model more interpretable, you use something. There's methodologies that are called SHAP methodology. These are some statistical methods that you will use in order to interpret the model, like what's happening with the data, what's the mean of the results, what the drifting that's happening in the results, are the results reliable, are the testing scores are coming perfectly. So all of these things that you can do. This is plus with the domain knowledge. Now, a new thing that emerged in the previous years, it's called symbolic regression. So what is symbolic regression? The symbolic regression is a subset of AI and machine learning. Basically, this symbolic regression, it will take your data, you'll just provide it with the data, and then machine learning will basically create an equation for you. And yes, machine learning nowadays can create an equation for you. So basically, they will take the data, they will try different things like multiplications, square roots, powers, exponential, and they will try to merge parameters, they will try to mutate some of the operations, and then you will generate something called a generalized equation. So that equation will help you also into interpreting the data. But keep in mind the equation that you get, so the equation that you will yield from symbolic regression must match with the three equations that I just presented which was the conservation of mass, the conservation of momentum, and the conservation of energy. Any equation that you get from machine learning that basically violates any of these phenomena, you can say that this is not correct, or you need to do your work one more time, or there is some hidden pattern that you did not know about. So we have different possibilities. Now let's start working with a real, yeah. So let me just prepare the data for you guys so we can start working on an example. So you don't, by the way, you don't have to understand what's happening 100%. The important thing is to understand the main workflow and how the data is being basically passed around and what are some of the things that I'm doing. So you don't have to learn 100%. The idea is just to show you what's happening. So first of all, let me create a Python file. And from this Python file, what I'm going to do is there is a single well log data. So this is what the data looks like. Now, this is the data. So we have the well log depth, we have the permeability, we have the porosity, and we have the shale volume, DT, gamma ray, and whatnot. So the most important thing is you have something called lithology. So based on these readings, so the engineer or the petrophysicist, he saw that these numbers, they best fit something called claystone. By the way, claystone is something similar to shale, or it's exactly shale. And we have some siltstone, we have some sandstone. So these are now these labels that you see, these are called labels. In oil and gas industry, we call these lithologies, but in machine learning and AI, these are called labels. So here is the idea. What I'm going to do is I am going to take these data, I feed this into Python. I will tell Python to learn based on certain parameters that I set, and then I am going to provide these parameters, and machine learning should be able to predict the type of the formation that it is. Okay, so this is known as lithology prediction. Okay, so first of all, number one, so by the way, I'm going to show you, I am going to give you a rough workflow this workflow is going to be fixed almost all the times that you're going to work with it. So this is going to be the most crucial thing. So the workflow goes like this. So number one is you set the problem at hand. So you need to understand what the problem you have. Number two, you need to define results you want to get. So these are very important. Number three, once you have these, you will start reading the data. Number four, you have to process the data, clean the data. Number five, by the way, let me show you something. This is going to consume somewhere between 60 to 80% of our time. So keep that in mind. So processing and cleaning the data, it's going to take really, really large number of times. Okay, so number five, once you do that, build the model, which is going to be the AI ML model. Number six, it's going to be train the model. Number seven, it's going to be test the model. Number eight, it's going to be plot and explore the results. By the way, in the process of reading data, the process of reading data can be further categorized into opening file, B, exploring the data, C, you can do a visualization, D, you can do lots of things that are related to reading the data. Anyways, this is the rough workflow that you will go and do. And this workflow is already mentioned in the PowerPoint that's going to be shared with you guys. So this workflow is this one. Let me show you. The workflow is this one actually. This is the detailed workflow that I just listed for you guys. Okay, so first of all, let's set the problem. Okay, let's understand what we're trying to do. So what's the problem at hand? So we need to set the problem. So my problem is, let's try to answer this. The problem is I have log data, and now what I want to get, I want to know the lithology. So this is the problem. This is the results that I am seeking. Now, once you have these two objectives cleared, now you can move forward by reading the data. Now, by the way, there are also other steps that are in between that I intentionally did not mention, like evaluating the model, like checking for data drifts, getting more test data, splitting the data. There are lots of normalizing the data. There are lots of things that I did not mention, by the way, so because I want to keep this simple. So first of all, let's do this. We need to start reading the data. Unfortunately, in Python, it's not possible to read complex data. So that's why we turn and use libraries like pandas. So import pandas SPE. So this way we are going to import pandas. Now this is going to help us reading the data. Now, what do we need next? We need to build the model, so we need that as well. So import sklearn dot decision tree, or let's do tree as tr. So this is going to help us to build the model. So do machine learning. So this is going to be read data. Okay. So this is going to help us read data, and this is going to help us to do the machine learning. Now let's read the data. So data equals to pandas.read CSV. Since this is a text file, so we need to use the CSV. Now the name of the file. Once we have the name of the file, we can progress forward, and let me show you what the results look like. You run the file. There we go. Now you have read the file. This file contains 13,000 rows with 12 columns. Okay, so the idea that we need to keep in mind that the column that of interest is called lithology. We're trying to predict the lithology based on what? Based on these columns, which is the permeability, the porosity, the shale volume, the sonic, and gamma. By the way, gamma ray and V shale, you will use one of these, and I'm not going to tell you why. You have to search for this information on your own. Either you use V shale or you use gamma ray. You cannot use both of these. You have to search why. You have the photoelectric, you have the bulk density, we have the resistivity. Okay, so by the way, there is also a certain approach in order to select these columns. Selecting the columns, it's not a guesswork, it's not something random. You have to know how to select columns. I'm not going to show you the process because that process can take some time because it's a multi-step process. Anyways, let me show you something. Let me show you some basic statistics of the data. So this is going to be data.describe. So this is going to show me some statistics. Once I do this, I know what is the count for these things, what's the mean, what's the standard deviation. By the way, the standard deviation is very important in machine learning because the more standard deviations you have, you mean the larger your data is in terms of spread. Okay, so the narrower standard deviation you have, it means the data is not spreaded very well. So that's going to be a question mark in the future usability of the equation or of the model. Plus you have the minimum data and maximum data. By the way, I usually check for these two things. I check for the minimum, I check for the maximum. So why do we need to check for the minimum and the maximum? Because the minimum and maximum is going to provide you the logical engineering sense in order to know if these data are correct or not. For example, I know that for sure my well is not deeper than, for example, 5,000 feet or 5,000 meter. But if you see depths like 50,000 or like 10,000, it means that the data is wrong. So based on these really simple numbers, you understand what's happening. By the way, if you're not comfortable viewing these inside Python, you can do to Excel. You can export these to Excel, and yes, Python integrate nicely with Excel. Let's do stats.xlsx. Let's run this. Now you can see you have an Excel that it with holding the same results. There we go. And in Excel, you can also do this. You can go to data and filter these out. And now you can do, for example, you can sort any of these values you want. By the way, you can also transfer these, or you can also transpose these. So you can do these lots of things with this. Anyways, once you do the statistical description, now it's time to start building the model. So start building the model. So in order to start the build a model, we need to define what variables that goes into training. So that's going to be what we want to train. So what we want to get. By the way, these green lines that you see, these are called comments. It helps you to understand the code better. But it's totally blind to Python. Python does not see these. So what do we want to train? So the train, we are going to set data that we want to train. So that's going to be data. So now we're going to select which data that we want to train. I am going to just select arbitrary values. I'm going to select, for example, shale volume, neutron phi, row bulk, and let's select the RT. So these are the X. This is what we are trying to train. So I am going to feed the machine learning or the AI these things, and I am going to tell the machine learning based on these data, what I want to learn or what I want you to learn is to know what are the corresponding lithology to these data. And of course, this is flexible. These columns are flexible as long as you're satisfying some of the concepts of column selection or feature selection. And of course, I'm not going to dive deeper into that. But keep in mind, we have multiple approaches into selecting columns. One of these approaches is the engineering common sense. So once we have the data that the machine learning is going to feed on and the data that we want to predict, now it's time to start building the model. So we will say that model or machine learning model equals to tree dot. Now we can select any model you want. We will select decision tree, and once we create our decision tree model, which is a machine learning model, we will say that fit. So fit is basically, it means that train the model. So once we do the fitting, so we will provide in the X and Y, we will run this. You will see that the machine learning started to train. Now the machine learning is trained. Let me show you the accuracy of the model. So accuracy. So let me print the accuracy. So we'll say the model.score. This is going to show us the accuracy. You can see the accuracy is 99%, but yeah, don't get happy. This is not a true accuracy because there are lots of missing steps that I did not do. For example, I did not split the data. I did not scale the data. There are lots of things I did not do. But yeah, this is the accuracy we got. We got actually 99% accuracy. So let's multiply this by 100%. You can see it's 99.99%. You can switch to other models. For example, you can see the model training the model was just 2 lines, but everything else took some time from us. So that's why 60 to 80% of the time you will spend is basically on these things. Now, let me show you how you can visualize the or let's say, let me show you how you can check for the lithology. Okay, let me do this. Import plotly.express as px. So let me show you. So plotly express dot. I'm going to do a scatter chart. So we're going to pass in the data, and we will say on the x-axis we're going to set, let's say that we want to set the bulk density. On the y-axis we want to set the depth. So depth is going to be data dot index. So actually, let's check this data. Yep, we have a depth column, so we are going to use that. So we will say that set the depth, run this, and there we go. Now this is what the log looks like. Now let's make sure that this is a little bit better than before. And let's make sure that the height for this log is actually this. Let's make sure that this is 2000 pixels, and the width is going to be 200 pixels or no more than 200 pixels. Run this. There we go. Now this is what it looks like. Yep, I think this is 500 is going to be okay. There we go. Now this is what our well log looks like. Now this well log is very bland. This is, of course, this is just density plot. You can also have other plots alongside with the density. For example, you can have the neutron phi plot as well. Neutron phi, that's also a possibility to insert that as well. You can have like any number of plots you want. Now the idea is let's switch back to bulk density, or we can also view the shale volume or VSH. Now this is the shale volume. By the way, shale volume is how much clay content you have. Now, what we did now is we actually created a model that learned the lithology. What I'm going to do is I'm going to show predicted lithology equals to model dot predict. I'm going to predict the lithologies for these models based on our X data. Let me run this, and now if I print the predicted lithology like this, you can see it started to predicting the lithology based on the data. Now it means that the machine learning is working. Let's put these back next to the original data. So data litho predicted. So now we are saving the prediction data next to the original data, predicted lithology. Run this. Now looks good. Let me show you what the data now looks like. Now the data now has a new column, which is called the predicted lithology. So this is the original lithology. This is a predicted lithology. And now you can start to compare. Actually, there are other ways also to compare. You can see it's basically successfully uh, predicting that this is clay stone, this is siltstone, and so on and so forth. You can also resample the data to get different columns, sorry, different rows randomly. So this is random rows we are getting. So you can see that sandstone, we have limestone, we have silt. Everything is being predicted properly. The more data you have, the more accurate the results going to be. Now, one final thing that we're going to do, which is going to add more explainability to our data, we will say that the color for these points are going to be based on the predicted lithology. Let's run this. There we go. Now these are the predicted lithologies. Let me zoom in. I think this 2000 is too much. Let's make this 1000. So this is the predicted lithology. You can see that the siltstone is in red, claystone is in magenta. We have limestone and whatnot. Let me show you what you can do. You can turn off everything and just keep the formations that you're interested in. For example, let's see where we have coal. So double click on the coal, you will see that we have coal on depth of 3000 something and something afterwards the 4000. Now let's say that where we have sandstone. So you can see there is sandstone all over the well. Let's see where we have limestone. You can see you have some certain areas that has limestone. You can also do the same thing for silt. You can also do the same thing for claystone. You can now filter these as you move forward. Now this was a something called classification. Basically, you will feed in the data and then you will retrieve some other labels as well. Of course, the more data you have, the better the results you'll get. And one final note, this is not a complete workflow. This is just an overview of what you can do. The complete workflow, it's going to be representing more data processing and more intensive data selection. And of course, much more important than that is more data inclusion. Actually, this is all what I have from my side. Thank you so much for hosting me. Now over to you, SPE guys.